Alright, welcome back to another episode of Torture. I'm some random dead person. Let's just get started and not waste any time. These are the data types we're going to be talking about today. We're going to be talking about nominal, ordinal, interval. We're not going to be talking about ratio because the doctors didn't talk about ratio. So let's be real, none of us care. I can make a bunch of jokes, about ratio and stuff, but cringe, move on. So this is nominal data type. Now, because I'm a nerd, I can immediately tell you that nominal uses the Latin root nom, which is name. And this is because this uses named categories. And these named categories aren't really ordered in terms of magnitude. This is where you get stuff like gender, discord rank, drug versus placebo, and so on. Now you can use numbers to represent these categories. For example, you can have 1 for placebo, 2 for drug, right? Now this can be binary, such as smoker or non-smoker, or it can have multiple categories, such as blood type, which politician the participant voted for in the past election, or so on. Now, nominal data types, you can't really average them. So, for example, you can't really find the average blood type, right? So if you average these four numbers out, you're going to get something like 5, right? Actually, you're gonna get 2.5 as your average, which that's not really like a rational blood type, right? No blood type is 2.5. Like, what is it between A and B? But it's also not AB. Like, that doesn't really make much sense, does it? But what you can do is you can get proportions. So you can say that 40% of the participants were blood type O, or 70% of the participants were cringe, or 130% of the participants voted for Putin in the past Russian election. So next we have ordinal, which uses scales that are ranked in order of magnitude. Now you can rank them in two ways. Either you can rank the data itself, or you can use some sort of scale. But when you do use the scale, it doesn't have to have consistent gaps between each of the respective. It doesn't have to have consistent gaps between each point, right? So let's look at an example. If you use a cringe scale from 1 to 10, the difference between cringe of level 1 or cringe of level 2 isn't going to be the same as between 3 and 4. And that's because it's a subjective scale, right? And another one is ratings on a Likert scale, or, for example, rating your pain on 1 to 10, since, most of you are probably very familiar with Pro. So let's look at this whole ranking system thing I talked about earlier. This is how to rank a dataset. Now, step 1 is you want to collect data. So in this example, we collected post-exam depression on a scale of 1 to 10, where 1 was no depression and 10 is keep on thwacking me with a spoon until I eventually, die from brain damage. So here's our example dataset, and then we arrange the dataset from highest to lowest. And then we can start ranking them, just like here on the table. So what you'll see is that there was more than one that had the same value. So in this case, 2 people ranked their depression level as 9. And so they both got rank 2. What this also means, though, is that we skipped rank 3 because 2 people got rank 2. Now, if you had 3 people that rated it a 9, you would then skip rank 3 and 4, and the next one would get a 5, and so on. And so this is something you want to be careful of. You might actually want to try practicing this a couple of times, just to make sure you have a good grasp of it, because it can get pretty confusing pretty quick, and it's very easy to make mistakes, because at some point you might end up like counting 17 of them. They do like to mess with us like that. I'm sure you have experience from last year. So just be wary. This is one of the ways they might try to mess you up. They might try to, trick you with this one. Then there's interval data, which is basically all of the proper measurements. This is age, height, weight, how many miles per hour were you going over the speed limit when the policeman caught you. Now this can be continuous, like height, or it can be discontinuous, such as, the number of children you had, or the number of bombs I planted beneath the university. Don't tell anyone. They're not meant to go off yet. And then we have time to event data. So this describes how long it took for an event to happen. But the interesting thing about this data type is that it's a hybrid. It has both continuous data and binary data. Now the binary part is, did the event happen? Yes or no? Now this is binary, right? It's nominal. And it also has continuous, which is, the time until the event happened. So, for example, time to death is one of the time to event, is one of the, is a time to event data. And so the way this works is we say, look at a patient, right? Did they die? Yes or no? Did they die during the study? Yes or no? And if they did die, when did they die? And so you can use this to go, oh, okay, so it turns out cyanide is in fact poisonous, and all of the patients didn't just randomly die of heart failure. Wow, that's wild. So, data types actually have a hierarchy. Now this is based on how much information that they store. So ratio stores the most info out of the data types, but again, nobody cares about ratio. Nominal stores the least amount of data types, which is which category is it in, and that's it. Now what you can do is you can downgrade data from a high data type to a lower data type. So you can downgrade interval to ordinal or ordinal to nominal. Now downgrading is useful for when you don't want the high precision, and it helps you group together a lot of similar data. So for example, we might want to convert age into categories. So you might convert, age, which is a continuous data type, into nominal data, which would, convert it into categories. So below 30, 30 to 50, and then above 50. Now, outliers. Outliers is a really big or a really small value that are really, really far from all of the other data that you collected. Now, this can be the result of errors while you are measuring, or it can be the result of, just some typing error, or, the fact that all of you are doctors and nobody can use their hand to write at all. But there is a chance that you just have absolute units that can defy all laws of physics. And because of this, you can't always remove outliers until you're sure that they're because of errors. Because, a lot of times we do want to look at, absolute physics-defying units. But if it is an error and it's not just some complete sigma male, you do want to get rid of it because it can manipulate the statistics a lot. But one other thing you want to be sure of, one other thing you want to keep in mind, is that not all of your statistics will be affected by outliers. So if you are suspicious that there might be an outlier, you might want to just be safe and use a median instead. So here's an example. You were asked to collect people's heights in uni. And here's the data you collected. So these are the data points, and you found that the average height was 5.7 meters. Now, clearly, that's a little off, isn't it? So you look at the data, and you found that this student over here is a whopping 29.9 meters, right? Which, that's like almost as tall as Rafi or something. But, clearly something is a bit wrong. And so when you looked at what the students did, you realized that one of them made a very, very minor error, and instead of looking at a student, he measured the length of a blue whale. Which, blue whales generally don't tend to go to university. They sometimes do, but generally they don't. And so you will want to remove that specific data point. Now, here are two ways you can identify outliers if you don't want to, manually check if every student was a blue whale or not. So you can use a scatter plot, which helps you visualize things very nicely. As you can see here, this point is really, really far away from all of the others. And, once you remove it, everything looks nice and clean again. Now, another way you can do is box plots. Box plots are very cool because, okay, they're not cool. They're cool for nerds because they help you mathematically identify which ones are outliers. And let's look at how to make them. Now, obviously, you'll probably just be using software because this is a lab session, but I don't know how the exam's going to be. In case you do have to do it manually, here's how. And you'll want to find these values. The 50th percentile, that's just a fancy word for the median. The 25th and the 75th percentile, and that's the 25th is your first quartile, the 75th is your third quartile. And then once you find the difference between them, that will be your interquartile range. And finally, the adjacent values. To find your adjacent values, you take your interquartile range and you multiply it by 1.5, which is this calculation down here at the bottom. So, again, let's take an example. Here are your heights. Let's just say you redid the experiment after kicking that whack student out, and you finally collected some proper data. You ordered them from lowest to highest, and then you found the median. Right, so the technique to find the median, let's just do this very quickly, is that you'll count these. Now, I already did this off camera because I recorded this like 17 different times, and basically there's seven data points on this in this experiment. Now, if we half 7, that's 3.5. 3.5, you round it up to 4. And so you want to count 1, 2, 3, 4. This is your median. 166, and there it is. Now, the 25th percentile, to find that, you cancel out, you remove your median. Okay? And then you look at this bottom half, right? And so you want to find the median of that. So there's 3 here, divide it by 2, 1.5, round 1.5 up, that's 2. So you count 1, 2, here's your 25th percentile. And there it is. Basically, you want to find the middle here, right? You can just see it visually because there's only 3 of them. And you do it again for this side. There's three data points here. Divide it by 2, 1.5. 1.5, round it up to 2. Then you go 1, 2, there it is, there we go. 187, here's your 75th percentile. Let me just tidy all of this up. Okay. Then you want to find the interquartile range. Which is just the difference between your 75th percentile and your 25th percentile. And here it is. 187 minus 157, so that's 187, minus 157, that equals 30. And to find adjacent values, remember that's just the interquartile range times 1.5. So that's 30 times 1.5 gives you 45. Now, to understand where this 1.5 came from, I'm just going to give you the simple answer. I have no idea. I just stole this from the PowerPoint, and I'm doing it word for word. Okay? And so let's represent all of this visually. Here's what it looks like visually. Here's our box plot. We have our median over here. And then we have our 25th percentile and our 75th percentile. And this creates our box. Okay? And then we have our mean represented by this dot. And in some cases, it might be represented by an X instead. And then we have this line, which represents our adjacent values. Now here it's saying that it's the 5th to the 95th percentile. I'm not exactly sure if that's the case. You might just want to check with the doctor. But on the safe side, I just followed this calculation since, again, I just completely ripped it off. Don't tell them, I don't want to get copyrighted, please. And then you'll notice that here we have 2 points that are outside the adjacent values. These 2 points are outliers because they're outside the adjacent values. But you'll notice that they are the 1st and the 99th percentile, meaning that there are genuine data points that are outliers. And that's why I said earlier that you always want to check if your data point is an actual outlier or if it's just some freak of nature, right? Like if you just invited Shaquille O'Neal by accident to your experiment. And so that's all for today. Or unless you're cramming like 2 days before your exam. So that's all for this 14 minutes. Go take a break and rest or something. Or go sleep. Up to you. See ya.